So rather a long title, and I mean basically this follows on from the previous presentation, and it's about the question of how do you connect everyone and everything everywhere. So we know terrestrial networks have done a great job in connecting a large proportion of the population, but they certainly don't go everywhere. So there we go. Here's an outline of the talk. So I'll start off a little bit about, there's a buzz phrase there, the digital divide, just to say a little bit about what that means. And the nature of the devices that are being connected is changing. It's not just mobile phones nowadays. With the Internet of Things, there's a wide variety of different devices which need to be connected. And they're not all in cities. This is one of the issues. A lot of the IoT devices will be distributed in fairly remote places. So there's a little bit of background on the convergence of the terrestrial and non-terrestrial networks, use cases, and then the role of, we've heard a lot about satellites, and satellites are always in the news, but high altitude pseudo satellites or high altitude platforms, I think will also have a very important role, and we'll talk a little about the benefits of using those. Then spectrum, there's a constant battle over spectrum. A lot of conflicting demands. You've got very hungry mobile operators wanting spectrum everywhere and as much as they can possibly get. And then the satellite people also trying to protect their spectrum. So I'll just talk a little bit about that. At the moment, WRC 19 is happening in Egypt, and there'll be doubtless numerous interesting discussions going on there over the next month. Then we'll talk a little about the challenges of RF technology, look at some of the physical issues that we have to face, the status of semiconductor technology and where it currently is to address some of these issues. And then I'll give some examples of some real hardware that we've built and is attracting a lot of attention in these applications. So, as has been mentioned this morning, at the moment, only about half of the world's population is connected. The coverage is actually better. So, in terms of places that have no coverage whatsoever, it's around about 1 billion out of the 4 billion Earth population. And the reason there may be coverage, but there's a lot of reasons why people don't take it up due to lack of local infrastructure, affordability, and relevant content. 5G is coming along, but it's estimated that even by 2025, I think the graph up there is right, it'll be about 34% of the global population have 5G. Then there's a quotation I've given here from the director of radio communications at the ITU, and he's saying there that there's this overarching ambition for 5G to cover everything and everywhere, and he's saying that rural coverage is going to be a major problem, and he sees a great role coming in for mobile platforms, HAPS, and satellites. But this will require a convergence of the network, so interconnecting the terrestrial networks with the non-terrestrial networks. So, the other point is, in terms of coverage around the world, there's a huge variation. So in the West, in North America and Europe, then you've got very high levels of coverage. But in the more remote areas in Africa and Latin America, then you're really down to quite low levels of coverage and usage. So I was saying a little bit about the nature of devices. So it's not all smartphones. The first graph there shows the data, the growth in data traffic by device type, and sure enough, smartphones are growing pretty rapidly. But it's interesting here, the machine-to-machine communication for IoT is also growing in terms of data rates significantly, but in terms of the number of devices, then they were estimating that over 50% of mobile devices will be of that form rather than phones and consumer type things. So we need to provide coverage for all different types of device. So there's a picture of what a converged network may look like. So it's I'm trying to show everything here. So satellites and interconnected satellites, very important. High altitude platforms or pseudo satellites, which could be in the form of lighter than air balloons, basically, or UAVs, sort of fixed wing aircraft. And they each have their own merits. But the idea is that there's a number of different uses. So we could imagine having essentially a base station serving directly users on the ground. It could be providing backhaul to remote areas, so local cells, which are then backhauled through HAPS or through satellites. And then Internet of Things, again, could be served by a base station on an airborne platform. So there's a wide variety of different use cases that are relevant. This is an output from a recent EU document, 5G study, and that's outlining the use cases for what they call enhanced mobile services. So again, multi-connectivity for underserved areas, connecting to trains and boats and planes, things that you're never going to connect, as has been said, with fiber. And these are all attracting more and more interest. So maybe enough of that. So in terms of HAPS and satellite synergy, so we've heard satellites are going to be transiting across the sky pretty rapidly. You've got satellites that are traveling at 7 kilometers a second, whizzing above. You have to be able to track those. So steerable antennas are absolutely essential. The high altitude platform is a different beast. It's got more persistence. It can be stationed reasonably statically over a certain area. Okay, it is moving slowly, but it's a much easier proposition to connect to a high altitude platform. They will be operating at about 20 kilometers in the stratosphere. So again, in terms of the path loss and the system gain that's required, it's a lot easier. So I think they can be seen as an extension to terrestrial networks, and can also be deployed very quickly. The good thing about the HAP is, the investment in terms of launching the thing is minute compared to putting satellites up. You don't need rockets. You basically need a canister of helium and a nice, shady, wind-free place to launch it from. So they're easier to launch. Once they're up there, they're probably only going to be in operation for maybe 3 or 4 months. So the lifetime of the equipment is less stringent, and they can be changed. The thing's not going to be up in the sky for years. So if you need to upgrade the equipment, or if there are issues with having to change the configuration, that can be managed. So I think they have an important role to play. And we've seen a lot of improvements in the technology that makes it possible. So this is a slide that I stole from ESA, and that's showing the two types. So we've got balloons, and there's a large, well-known company that's already deploying a balloon-based network, and that is providing service in countries in South America and Africa. A bit further out, there are the fixed-wing aircraft, and again, we've seen examples of these operating over quite significant times now. The difference between the two is that the payload on the balloon is quite significant. They've got a pretty good lifting capacity, and they can accommodate a large number of solar cells to power it. The fixed-wing aircraft is more challenging, so the payloads are smaller, and obviously where they can operate in terms of latitude and so on is probably more restricted. But they are developing, and they will have roles as well. Okay, so moving on. So spectrum, there's this huge debate going on. So we've got 2 or 3 different factions all battling out to try and reserve their chunks of spectrum. And these are a few quotes just leading up to the WRC conference that's going on at the moment. So we've got the mobile operators insisting that they want to take virtually every chunk of spectrum that's available. You've got a lot of concern amongst the satellite operators in that they've been identifying millimeter wave bands to ensure that the capacity of the satellite networks can keep pace with what's required, and those bands are also now overlapping with a lot of the mobile bands. Then throw HAPS into the mixture, that upsets both camps, because the satellite people want to protect their bands. Again, they overlap. And the frequencies also overlap with some of the backhaul frequencies that are used for mobile networks. So these are some of the bands that are being discussed at the moment. So we've got mobile here, and then we've got HAPS and fixed satellite service. Then there's also inter-satellite links as well, which are perhaps less of an issue. So there's new bands being identified. If we look at HAPS, at the moment there are some very narrow bands identified. Round about 48 is a current band. There's a move to extend to open up a much wider band around about 39 gigahertz. And then in North America, there's another band down at 26 or 27 gigahertz. I'm going to mention E-band here because I have a vested interest in E-band. It's not strictly allocated for high altitude platform use. There are bands for fixed service satellite in E-band and higher, in fact. But the fact of the matter is this band is being used. There are experimental licenses, and there's quite a bit of work going on using E-band. I'll explain a bit why there's some interest in that. And then high throughput satellites, again, they're trying to extend bands. So we've heard that what they term V-band, which is really the lower end of V-band, around about 50 gigahertz. There's a desire to add another couple of gigahertz onto that, so that you'd have two quite large usable bands for high throughput satellites. And then on the mobile, there's this sort of grab for anything that's available. E-band here is used mostly for backhaul, although there are people thinking that they maybe could use that for access as well. I'm not too sure about that. There's also the V-band, the unlicensed band, which has now been extended up to 71 gigahertz. But again, there's some debate as to whether that should be kept as a completely licensed-free band or whether that could be allocated for mobile access. So again, there's a lot of discussion over that. So let's just look at some of the applications and what's involved. So if we break it down into feeder links and into satellite or into HAPS links. For the feeder link, I mean, we've got a platform that's at 20 kilometers in altitude, and the typical area that would cover would be around about 70 to 80 kilometers in diameter. So we're talking about elevation angles of about 30 degrees. Now, the bandwidth that's available that's already been allocated are these ones in blue, so 6 gigahertz, 28 and 47. And they're reasonably small bands. You know, there's not a huge amount of spectrum available there. The 38 gig band will be significantly wider. You know, there's over a gigahertz of bandwidth there. But it all pales into insignificance compared to the amount of bandwidth that could be used in E-band. Now, one of the big challenges, of course, is for all of the frequencies above 40 gigahertz is rain attenuation. So this is the typical type of attenuation that you get per kilometer versus frequency. So for most of North America and Europe, we're talking about 42 millimeters per hour is the sort of the worst case that you'd get for 99.99% availability. So these attenuation levels do present a huge challenge to millimeter wave. But the thing to consider is that the availability that's demanded for this type of application could be a lot less than the 99.99 or 99.99% that you might want from a mobile phone network. We're serving areas that have got nothing, so you know, getting 99.9% could be seen as to be quite acceptable. So this one's a bit busy, but I thought I'd just compare. If we look at the bandwidth that's available for the various HAPS bands, so 31, 39, 48, etc., and compare the sort of data rate that could be achieved. Because of the limited bandwidth, even if we operate at a fairly high modulation level, to 256 QAM, then you're limited by the bandwidth there to around about 1.5 gigabits per second. If we operate E-band over 2 gigahertz channels with 256 QAM modulation, then we've got a 10 gigabit per second capability. But of course, you have to allow for fade margin for these things, and these are fairly moderate. And I've just done a calculation there based on a typical rain height and slant angle. So you can see that the fade margin is reasonably sort of useful for a moderate availability. And then it's interesting for us as to what sort of power we need to deliver in our transmitters. So the power levels I've used here are, again, very achievable. 26 dBm at E-band, going to maybe 35 dBm down at 31 gigahertz. The interesting thing I've found really is if you compare the data rate, we could drop the data rate down on E-band to QPSK, for example, and we could still get quite a useful data rate, 2.5 gigabits per second even, on a 2 gigahertz channel, compared to, again, it's still competing with the 48 gigahertz band. And then in terms of rain attenuation, even at 256 QAM on the rain path length there at 48 gigahertz is around about 2 kilometers. If we drop the E-band down to QPSK, then we get a 19 dB improvement in carrier to noise ratio, and therefore you get a similar sort of margin and similar data rate. So I thought that was quite interesting. Right, the other thing is, we'll see a bit later on, links between platforms is very important. And the propagation situation is much more healthy here. You're above all of the rain and the cloud. And so you could support links of hundreds of kilometers. Even if we just look at the limitation, obviously the distance is going to be dependent on the ceiling of the clouds and the rain height. So if we look at what would be cloud limited at 20 kilometers, you've still got a link that could be nearly 600 kilometers long. If it's rain, if you want to keep away from the rain, it could be 800 kilometers. So these are substantial links, which gives some flexibility in the way the networks are designed. Again, apologies for the number of figures on here. This is looking at the system gain that would be required for an inter-HAPS link. You still have to consider some atmospheric loss, but at altitude it's substantially less than it would be at sea level. So these are the curves you will typically see for atmospheric attenuation versus frequency. It only usually goes up to about just under 9 kilometers in height, which gives the attenuation. There's within the ITU that they look specifically at the 60 gigahertz band because, of course, that suffers severely even at high altitude from atmospheric attenuation. But you can see at 48 and 70 gigahertz, then atmospheric attenuation becomes pretty negligible. So it looks, again, I've plotted the power that would be required from the transceiver versus two typical situations here. So 45 dBm RX sensitivity would correspond to a 256 QAM link. 56 would be more like 16 QAM. And then assuming 2-foot antennas, you can still meet the sort of 200 to 600 kilometer links with a perfectly realizable level of RF power. And in fact, as the frequency goes up, if you keep the antenna size the same, then you do get a benefit from the extra gain from the antennas. And in fact, it's doubled because you get that benefit in both the transmit and the receive. So if we compare that now to the low Earth orbit satellite situation, so here the LEOs, or what they call VLEOs, which is one of the orbits that SpaceX is talking about, they're operating at between 350 and 1,100 kilometers. Again, using some of the examples that I've seen in publications, they're looking at elevation angles around about 35 degrees. So that gives you a path length of about 600 to 1,700 kilometers. So that obviously is a lot more challenging. So if we look at the free space loss here, I won't even talk about rain attenuation on these ones just at the moment, but the free space loss compared to the HAPS is, tens of dBs different just because of the distance. I've also shown here the bands that have been available. So we mentioned what's termed V band here, 50 to 52 gigahertz is an extension that's also being talked about. Uplinks at 47 to 50 gigahertz and downlinks at 37 to 42 gigahertz. So in terms of free space loss, then obviously as the frequency goes up, it does become more challenging. So the next one here shows the system gain that would be required for a link from a ground to a low Earth orbit satellite. And again, interested to know what sort of power that we'd have to generate to make these feasible. So I've looked here at the path lengths, 600 to 1700 kilometers. And with no rain, then again, perfectly realizable sort of power levels of the order of certainly less than 40 dBm would suffice. And with antenna gains round about 58 dB, which, around about 1 meter at the higher frequencies. Now, if we put rain into the equation, then we all of a sudden get a system gain that is up, 240 to 250 dB, which is obviously going to be quite a challenge. So the way that this is being addressed is really considering the geographic distribution of the ground links. So they could be thousands of kilometers apart. So really, if we've got a network on the ground of ground feeder links, the likelihood of having a complete blockage in a particular area or in many areas is quite remote. So we're seeing some pretty clever software-defined network technology now being applied to non-terrestrial networks. So that you could network the satellites or the HAPS or both together. And with what they call, I think machine learning is the term that's been used, and software-defined networks, then this is really the way to overcome that. So just trying to battle your way through atmospheric attenuation and rain is probably not going to be practical. And the resolution will come by clever network technology. Right, just a bit about technology in terms of semiconductors. It would be nice to think that we could use gallium nitride, but really at frequencies above about 40 gigahertz, it's quite rare to find commercially available GaN. Certainly up at E-band, it just hasn't happened yet. So we're really in both Ka and V-band. GaN is okay at the lower end of that. When you get to V-band and E-band, then we really are relying heavily on gallium arsenide technology. One way around this, you might think, is phased array antennas. You obviously get considerable antenna gain, so you can get much higher ERP from a phased array antenna. So this plot here shows number of radiating elements versus ERP, and it goes as 20 log of the number of elements, so that you get a dramatic advantage there. The issue, of course, is in terms of element spacing. So when we get to the higher frequencies, we're talking about half wavelengths, which are going to be quite challenging to realize in any practical form. Again, looking at where you can get to with the different technologies. So with GaN, say you could have 30 dBm as a radiating element. With CMOS, you might be down to 0 dBm. So to get the sort of 60 dB EIRP that you'd need, you're talking about thousands of elements, which is possible with silicon technology. But the other thing is in terms of power consumption. So this, again, is fairly well used slide here, but it shows the trade-off between the number of radiating elements and the power consumption. So there's a sweet spot, really. Power consumption decreases simply on the transmit side as the number of elements increases. But bear in mind that each of those elements has a receiver behind it, and therefore that's a fixed amount of power. And so when you do the sums, as you increase the number of elements, the power consumption increases. So GaN and gallium arsenide seems to be the technology that would give the optimum efficiency versus the number of elements. But then again, the trade-off is in terms of element spacing. So I think from what we've heard this morning about different means of doing steerable antennas, then that's one of the challenges that maybe can be addressed from that. Right, so I just thought I'd show some practical hardware. This is a typical payload that you would expect for a satellite or a high-altitude platform, where you would have transceivers dealing with the inter-platform links, and also a transceiver dealing with the ground link. So each payload would essentially have three transceivers, plus a base station, an E node B or a G node B, depending on whether it's LTE or 5G. Again, steerable antennas are essential. For high-altitude platforms, then the gimbal-mounted parabolic antennas are actually widely used, and because they don't have to scan quickly, and you've got the ability to carry the payload on a balloon, then they are quite widely used. So just looking at inside each of these transceivers, in its basic form, this is what we have in our Morpheus unit. These are used in mobile backhaul. This is an E-band example, and inside there we've got a direct conversion up converter for the transmitter, a power amplifier with power detector, a direct conversion down converter receiver, and then the local oscillators and filtering to provide the carriers. We also need a diplexer. Most in these type of systems, they're usually FDD, so we have separate transmit and receive frequencies. So this is our Morpheus unit. So this is completely integrated. All of these functions are contained essentially under this box. The rest of it is power supply conditioning and control. And then the diplexer is actually integrated into the base of the transceiver. If we need more power, there's an example here of perhaps a slightly brute force way of doing it, but using power combining. Now, the beauty of working at millimeter wave is that you can do very efficient power combining in waveguide, and it is a manageable size and weight. So this is an example of a four-way power combiner. Are we running out of time? All right. We'll move on. So there's lots of results. You can see those in the slides, but we've demonstrated 2 to 3 watts power combining in these amplifiers. The interesting thing here is the power combining efficiency, which somewhat surprised us, is that in a single amplifier we're getting about 24 or 25 dBm, but this would imply that there was virtually no combining loss. So I think this is probably really down to the mimic variation and the difference in matching, but the power combining is surprisingly efficient. I'm going to skip through the results and let's look at some more chunky things here. This is our transceiver combined with a power amplifier. So these are used in long-range links. It can cover many tens of kilometers. And then I'll move on. This is what we did in an inter-hap link. In this case, you have to be able to switch the duplex spacing, so you don't just have a fixed duplex at one end and the opposite at the other. Each end has to be able to swap its duplex arrangement. So it becomes a little bit more complicated. And then if we want very high data rate, this is an example of a 4-channel system here, which has got 4 transmit blocks in it, 4 receive blocks. They're combined through a multiplexer and then fed to an OMT and a polarizer. So here we can actually achieve 40 gigabits per second, and this is real. We've developed this, and it's been trialed in real applications. This shows how we get the channels combined. So from the multiplexer, we have transmit and receive on left and right hand polarization. At the receiver, it's fed through horizontal and vertical polarization from the OMT. This is the channel plan. So the diplexer is the multiplexer is quite demanding. We've got 4 separated channels here. each 2 gigahertz wide. There's some numbers there, we can come back to that. Just to show that it's real, there's a photograph of an actual 4-channel E-band transceiver. Each channel is transmitting about 2 to 3 watts, and that's operated with 40 gigabits per second links over, in the trials, up to maybe 20 kilometers at the moment. But that's where we are. And I think to summarize then, it's clear there is a role for non-terrestrial networks, and they will be blended with terrestrial networks to address some of the demands that are expected from 5G. Okay, thank you.